Welcome to the next video in the group theory series. In this video, we finally get down to business. We start proving things about all these damn objects that we have now. You can see here a preview of what we'll be discussing in this video. The theorems in this video are mostly united by the theme, proving things that just make sense, things you would kind of expect to be true. So, as I think, a fairly compelling first example of that, let's prove that the identity is unique, right? That there is precisely one identity in any group. Of course, for any group, there is some identity element guaranteed by the definition of being a group. We will prove, moreover, that there can't be more than one, I should probably spell that out, one identity element of any given group. More precisely, we will show that if there is some other identity, let's write it as the numeral 1 prime in G, then the first identity, the main one that we know to exist by definition of G being a group, must be equal to that one. So 1 equals 1 prime. What this really says is that, in fact, there really was just one identity all along, right? That if you find any identity, it's always equal to that one. So for the proof, assume that there is some 1 prime in G which is an identity, which means, by definition, that for all group elements, 1 prime x equals x1 prime equals x. We apply this with x equal to 1, so that we get 1 prime 1 equals 1. Symmetrically, we write out the definition of 1 being an identity element, like here. Now plug in for x equals 1 prime, we get this equation, very similar to the previous one. These two equations can be chained together to get this, which demonstrates that 1 equals 1 prime QED. We prove next a very similar theorem, which is that inverses are uniquely determined. So we know, again, by definition of a group, that for any group element G, it has an inverse, but we're going to prove that there can't be more than one inverse. And the proof is going to be very similar to the previous one in that we will assume that there is some other H in G, and which is an inverse of G, and prove that H equals G inverse. So let H be an element of the group, which is an inverse of this little g, also an element of the group, so that by definition of what an inverse is, if you product G and H together, you get the identity. Well, therefore, I could take this equation, especially I'll just select out this one, this part of it, and multiply on the left of this equation by G inverse, right? After all, if this just is the same thing as that, then when I take G inverse times that, it should be the same as if I just replace GH with what we know it to be equal to, which is 1. And on the other hand, right, this part here, this G inverse 1, clearly, just by the definition of the identity, that's equal to G inverse, sure. But also over here, G inverse G, that's the same thing as 1. So these two elements cancel, leaving 1H, which is to say H. And we also already observed that the whole thing is equal to G inverse. So we have that we have that H equals G inverse, QED. Next, we prove a law for double inverses, a very intuitive law, that G inverse inverse just is back to G. So let little g be any group element, and to show this claim, we need to demonstrate that G here, just plain G, satisfies the defining property of the inverse of G inverse, right? So for G to be this thing, That is saying that G is the inverse of G inverse. What does it mean to be the inverse of anything? It means that if you product them, you get the identity, right? That is the defining property of being the inverse of G inverse, is that if you product them, you get 1. So how do we know that this equation is true? Well, of course, uh, this is just immediate from the definition of G inverse, that G inverse would equal 1. So we know that this is true, and this is precisely what we needed to show that G has the defining property of being the inverse of G inverse, QED. Okay, next we prove that the product inverse, that is to say, the inverse of the product of some two elements, arbitrary group elements, G and H, is equal to the reverse inverse product. So reverse because they swap around, right? G was on the left, now it's on the right, and likewise for H. And then we are inverting each one individually and then taking their product. That's the claim, that these two things are equal. The proof is similar in style to the previous proof, which is that we show that this thing has the property which defines the inverse of that thing, GH. So we show that it has the defining property of the inverse of GH. This is the property that if you product it with GH, you get 1. That's the defining property of the inverse of GH. So we need to show that this equation holds. But through just a couple cancellations, we get it pretty quickly, right? These middle two G inverse G's cancel to 1, and then the 1 can just disappear, and then HH inverse turns into 1, and we're done. QED. Should have wrote it here. QED. Finally, linear solutions. So what am I saying here? I am making the claim that if you pick any two group elements, G and H, and you set up this equation with X like an unknown value, that there always exists a solution for X. That means, right, what it means to be a solution for X is that there exists some group element which satisfies this equation. So that's the claim, right? If you pick G and H, there always exists an X which satisfies this equation. That's the claim. Okay, the proof does what you might expect, which is to say that this equation is equivalent, right? It holds if and only if you multiply both sides on the left, let's say by G inverse, right? To get G away here, we multiply on the left by G inverse, and we get that these two cancel. And then you see the solution for X, right? Now, I could be a little more thorough in explaining exactly why these biconditionals are biconditionals. I think the reason why it goes from left to right is pretty obvious. Why it would go from right to left is possibly a little less obvious, but I'll leave that for the viewer to fill in. But if we assume that this has successfully concluded the proof, then notice that this not only shows that X equal to G inverse H is a solution, but in fact it shows that it is the unique solution because something solves it if and only if X is equal to G inverse H.